Hello, greetings to everyone and welcome to this video on my YouTube channel in which we are going to be talking about differential equations in further mathematics. So now into this video I am going to be explaining the concepts that you need to know to be able to resolve a differential equation problem, and in the subsequent video we shall be answering past or GC questions on the topic differential equation. So now let's get started. Let's discuss what a differential equation is. So what is a differential equation? A differential equation is any equation that relates a variable x and a function y, where the function y is a function of x. So the differential equation will relate a variable x and a function of x. Then its successive derivative, meaning that it will relate y to y prime to y prime prime, y prime prime prime, right up to y to the power n, which is a prime. So now it relates it to the first derivative, second derivative, third derivative, and so on. So that is the type of equation that we call a differential equation. Now let's talk about the order and the degree of a differential equation. We have first order differential equations, second order differential equations, third order differential equations, and so on. Now, how do we know the order of a differential equation? The order of a DE is the highest derivative in the differential equation. So if the highest derivative in a differential equation is 2, then it is a second order differential equation. If the highest derivative is 3, then it will be a third order differential equation. What about the degree? The degree of a differential equation is the highest power of the highest derivative. So for example, if the highest derivative in a differential equation is second derivative, let's say it is a second order differential equation, then we look at the power of d square y by dx squared. If the power is 1, then it will be of degree 1, or the second degree in case the power is 2. So now we check this degree only when the differential equation has been cleared of all radicals and fractions so far as the derivatives are concerned. Then we now look for the power, the highest power of the highest derivative. So now let's look at some examples. Example 1, we have this example on our screen. So let's look at this example. What is the order of this differential equation and what is the degree? The order of this differential equation, we can see that is 2 because the highest derivative here is d square y dx squared. So it is second order differential equation. What about the degree? What's the power of d square y dx squared? The power is 1. So it's a first order differential equation of degree 1. Let's go to the second example. Alright, we have the second and third example here. Let's look at the highest derivative. This highest derivative here is still 2 because it's a second order. This is second derivative here, which is the highest derivative. So this differential equation is a second order differential equation. So the order is 2. What about the degree? The degree is 1 because all this has a power of 1. Now, what about the third example? The order of this differential equation, the highest derivative is 5. We have the 5y by the x to the 5th. So this differential equation is a 5th order differential equation, and the degree of this the differential equation, because of the limit function here, is on infinite. Yes, it has an infinite degree. I'll take the third example, which is going to be the last example. Now we have such a differential equation. The degree is going to be 1, and the order is going to be 1, and the degree is going to be 2. The order, the highest derivative, is the first derivative. We can see here, this is the first derivative, the highest derivative, and the highest power is 2. So it's a first order differential equation of degree 2. Alright, now let us proceed to some exercises I am leaving you with these exercises for you to take from number 1 to number 3. Write down the order of each differential equation and equally write down the degree. If you're convinced of your answer, then fine. If you do that and you're not very certain or sure of your solution, then you can comment. You can send your solution in the comment section, your answer in the comment section, and I will verify if they are correct or not. All right. Just after the exercise, let's talk about exact and homogeneous differential equation. What is an exact DE? What's an exact differential equation? And what is a homogeneous differential equation? An exact differential equation is one whose differentiated function can easily be identified. So, if in a differential equation, the differentiated function can easily be recognized, then we have an exact differential equation. For example, we have this 2x dy dx plus y squared equal 7x minus 8. This differential equation is an exact differential equation because the left hand side is easily recognized as a differential equation in a differential equation of xy squared. Let's try to differentiate xy squared with respect to x. We are going to have the left hand side of this differential equation. So the differentiated function is xy squared. When you look at a differential equation and you are able to identify what has been differentiated to have this, then it is an exact differential equation. So we can write that d by dx of xy squared is equal to 7x minus 8. This is the differentiated function. So this differential equation can be rewritten like this, and therefore that's why we call it an exact differential equation, because the differentiated function can easily be recognized. Now let's talk about a homogeneous differential equation. What is a homogeneous differential equation? It is a differential equation that a homogeneous differential equation is one, or a differential equation is said to be homogeneous when the function y and its derivative appear in all the terms in the first degree. That means all the derivative appear to the power of 1. So we call it a homogeneous differential equation. In all the terms, the function itself and all its derivative appear in the first degree, that's to the power 1. All right, so these are some examples of homogeneous differential equations. All right, now let's talk about before we move further, the homogeneous equation associated to a known homogeneous differential equation is obtained by neglecting all terms which do not contain y or any of its derivative. For instance, the homogeneous equation associated with the differential equation xy prime prime plus 3 into y prime minus 2 is equal to 4x e to the 2x to the power 2 is going to be xy prime prime plus 3y prime equal to 0. We simply just neglect anything that does not contain the function or its derivative. For example, when we open this off, we're going to have a certain negative 6 somewhere. We flip it away because it does not contain the function, neither its derivative. So it is going to be the homogeneous equation associated with the non-homogeneous differential equation. All right, I think this is going to be the last part of the video. I'm going to be talking about the techniques in resolving a differential equation problem. How can we resolve a differential equation problem? It depends on the order of the differential equation. It could be a first order differential equation where we can solve easily by the variable separable method of solving differential equation, provided it is a first order differential equation. Now let's talk about the variable separable method. These are differential equations of the form f of x, y, and y prime equal to 0. That is, we can use the method of variable separable. if y prime or dy dx is a quotient, or it is a function divided by another function, then we can separate the variables and we integrate. We simply separate variables and we integrate, and finally we have solved the differential equation. We shall see examples when we get to solve past GC equations on the topic differential equation. But now you can use variable separable only when you have a first order differential equation. Now there is a second method of solving differential equation, which is known as the variation of constant. The variation of constant. Let's consider this differential equation: a of x y prime plus b of x y equal to c of x. A of x, b of x, and c of x are three functions of x. So now if we want to use the method of variation of constant to solve this differential equation, we are going to have the solution in two major steps. In step 1, we solve the homogeneous equation that is associated to this differential equation that we are talking about. So now the homogeneous equation associated to this differential equation is going to be equal to a of x y prime plus b of x y equal to 0. Remember, we flip off anything that does not have to do with the function y or its derivative. So now here, when we do this, we can simply separate the variables, and we use the variable separable method. We separate the variable and we integrate. In step 2, we then solve the complete equation: a of x y prime plus b of x y. I think I should indicate a of x y prime plus b of x y equal to c of x. Yeah, and let me read this. We do this by considering the constant of integration in our solution in step 1 as a function of x. Now we find y prime from the solution in step 1. We then replace y and y prime in the complete differential equation to obtain a new differential equation being a function of our constant of integration and its differential. We solve this equation for the constant of integration as a function of x and replace the solution in our solution of the homogeneous equation in step 1 to obtain the final solution. Alright, now let us proceed to talk about the method of using integrating factor. The use of integrating factor to solve a differential equation. Let's consider the differential equation: a of x y prime plus b of x y equal to c of x. In step 1, we make the coefficient of y to be unity. What is the meaning of that? We make the coefficient of y to be 1, meaning that we divide all through by anything that is like the coefficient of y. We divide here. We also ought to have divided here. So this will be c of x divided by a of x. Yes. Alright, so we make the coefficient of y to be coefficient of y. The coefficient of y here is b of x. Is b of x. So we ought to divide all through by b of x, which have made an error here to divide by a of x. We make the coefficient of y to be 1 by dividing all through by the coefficient of y. And when we do that, we have an equation. Let's call it equation 1. We are trying to call it equation 1. And then this equation 1 is called the standard equation. Now, when we are done with that, we go to step 2. We obtain the integrating factor. The integrating factor is gotten by taking e raised to the power the integral of the coefficient of y with respect to x. So we integrate the coefficient of y with respect to x. We take e raised to the power the integral of the coefficient of y with respect to x dx, and that we have the integrating factor. Once that is done, we can go to step 3. In step 3, we multiply the standard equation. Remember, equation 1, we called it the standard equation. You multiply that equation 1 by the integrating factor. Now, recognize that this resulting equation is exact. is an exact differential equation, with the left hand side being in the form d by dx of ye to the integral of the quotient of y dx. So that is it, how we can solve a differential equation by the use of the integrating factor. We shall see example when we begin solving our past GC question on the topic differential equation in our next tutorial. Alright, now let's talk about second order differential equation. We have seen how to solve differential equations in first order. The second order differential equations are differential equation in which the highest derivative is 2. It's a second derivative. So we can have we are going to have differential equations that are in the form f of x, y, y prime, and y prime prime equal to 0. So let's say we have, number one, we have equations of the form y prime prime equal to f of x, meaning that d2y by dx squared or d square y by dx squared equal to f of x. Now, we can solve this kind of differential equation by integrating. Like we integrate twice. We can integrate both sides of the equation twice. If y prime prime is equal to f of x, then y prime is equal to the integral of f of x, which is going to be another function plus k. The integral of f of x is going to be a certain function plus k, which is the constant of integration. And that constant of integration would be a certain real number. Then now, if we have y prime as the integral of f of x, then y will be the integral of f of x dx. So that means that we have double integral. In such a case, we integrate twice. Now, let's take case 2. Equation of the form x, y prime, and y prime equal to 0. Here, we use the substitution u of x equal to y prime of x to obtain the first order differential equation in u of x. Once we obtain that, we solve for u of x. Solving for u of x, we obtain y. This is usually useful when we have variable coefficient, that is ax prime prime plus bx prime, axy prime prime plus bxy prime equal to c of x. Now, when we have variable coefficient like a of x prime, a of x, y prime prime, and so on, then we can use the substitution of u of x. Now, what if we have the equation of the form my prime prime plus py prime plus qy equal to f of x? This seems to be the highest, the most difficult differential equation to solve for some students. But now, when we are going to be solving problems in the next tutorial, you shall see it being very simple. It has just two main steps in solving such a differential equation. Here, our complete solution comprises of two parts. The part 1 will be the complementary function, and part 2 will be the particular solution. So let's take A, the complementary function. It is the solution of the homogeneous differential equation of the equation that has been given to us. Let's say equation E. Now the complementary function, let's consider a differential equation. ny prime prime plus py prime plus qy equal to 0. This is going to be, if this is a differential equation, then the characteristic equation of this differential equation in equation 1 here, in this equation 1, the characteristic equation is going to be nu squared y squared because we have prime prime. Prime prime means the second derivative. So nu squared plus pu plus q equal to 0. This is the characteristic equation. Equation 2 is the characteristic equation of the differential equation in equation 1. Once that is done, we observe that the characteristic equation is a quadratic and it has a determinant. We know that the determinant of a quadratic equation is given by b squared minus 4ac. So now we observe this determinant. This determinant can be greater than 0, it can be equal to 0, or it can be less than 0. Remember, when the determinant of a quadratic equation is less than 0, we have complex roots. When it is equal to 0, we have real and equal roots. When it is greater than 0, we have real and distinct roots. So let the determinant in Roman 1, let's say we are looking at the determinant being greater than 0. Then our differential equation or the characteristic equation will have real and distinct roots. You have two roots that are real and different. Let's say the roots are alpha and beta. The roots are alpha and beta. Then now our complementary function yc is going to be ae to the ax to the alpha x plus be to the beta x, where a and b are real numbers. So now we have that the first root is alpha and the second root is beta. We simply substitute the first root and the second root in this equation of yc. Now what if the determinant is equal to 0? It means that the characteristic equation has real and equal roots. So the two roots are real and they are the same. We have alpha and alpha. So in the case of a real and equal root, yc has the equation a plus bx, or that times e to the power alpha x, where alpha is the root. Now let's talk about it when the determinant is less than 0. Here we are going to have a complex root, and the complex root here is going to be alpha plus I beta, or alpha plus beta I. Now alpha plus beta I, and we have the complementary function yc as e raised to the power of the real part of the root x, alpha x. The real part of the root here, we have alpha plus beta I. The real part of the root here is the part that does not have I, which is alpha, and the imaginary part is beta because beta is attached to the I. Okay, so now we have yc as e raised to the power alpha x, or that times a cos beta x plus b sine beta x, and that is it, where alpha is the real part and beta is the imaginary part of the complex root. Well, let's proceed. Let's proceed now to part B, which is going to be the particular integral. Like I said, to solve such a differential equation, it involves two steps. We have to find the complementary function, and lastly, the particular integral, yp. So, referring to this differential equation, which has an auxiliary equation of m squared plus mu squared, let's say mu squared plus pu plus q equal to 0. That's the auxiliary equation of this differential equation. Or we can say mx squared plus px plus q equal to 0. Yp has the following solution for this kind of differential equation. I'm going to present it in a table. On the left hand side of my table, I will have f of x, and on the right hand side of my table, I'm going to have yp, which is the particular integral. So when f of x is equal to 0, what is f of x? I'm talking about the right hand side now, the right hand side of my equation. if it is equal to a constant, then my particular integral will equally be a constant. If it is equal to a linear equation, px plus q, then my yp will equally be a certain linear equation. I say lambda x plus mu. Then if it is equal to p sine ax, meaning that it is is having a trigonometric function, my yp will be equivalent to yp equal to lambda sine ax plus mu cos ax. Now, if I have a quadratic function on the right hand side, then I'll equally have a quadratic function as my yp. Now, what if I have such an exponential function on the right hand side of my equation? I mean f of x. If I have an exponential function like this, pe to the power ax, I will have lambda e to the power d times e to the power ax, where d is the degree of multiplicity of alpha in the characteristic equation. We are going to see this more in solving problems. Now, ladies and gentlemen, here we come to the end of this explaining video on differential equation. Now watch out for the solution to past GC questions on the topic on differential equations on my YouTube channel. If you have not yet subscribed to this YouTube channel, do well to subscribe, like the video and share, and keep waiting for the next video, which is going to be solution to past GC question on the topic differential equations. Please subscribe. Thank you for watching.